Hello everyone, welcome to this beautiful Approaching High Energy Physics series brought to us by the Tamil Nadu Science Forum and the Saha Student Circle. So this has been a very collective group effort, and I'd like to thank every speaker who partook in this journey. And let me walk you through how it goes. We start with one lecture, the first lecture on the basics of particle physics and what's going on in CERN. We then dive right into the group theory aspect of particle physics. So here we discuss the basics of group theory and a little bit of representation theory and rotation groups that will be essential when we try to understand the quark model and various other ideas such as charge conjugation, parity, and CP violation, and the TCP theorem. And in lecture 3, we briefly discuss the various relationships between non-relativistic quantum mechanics and particle physics. We start with the Schrödinger equation, and then we head to discuss two particle bound states, the hydrogen atom, positronium, quarkonium, and about mesons, baryons, and their magnetic bonds. But also along the way, we do talk a little bit about the Zeeman effect and hyperfine splitting and so on. A few niche effects that are brought to us by either relativistic corrections or by means of quantum corrections to existing electroclassical phenomena. Then we try to dive deep into scattering. Here we first encounter the idea of cross-section, and we try to look at the classical case, which we've all encountered in one form or the other, such as the collision of two billiard balls or two boxes or cars. And then we try to place it in the quantum mechanical sense and the idea of this unit called Born and why it's essential for us. Then we sort of drift away to understand the different ideas about behind scattering, that is. So these include partial wave analysis, phase shifts, and what is called the Born approximation, the Born series, and how the Born series gives rise to Feynman diagrams. We'll also apply this in a few time models such as Rutherford and Yukawa scattering, and we'll examine what they mean for lifetimes of particles and how this all can be generally summarized by Fermi's golden rule. Then we head over to Feynman diagrams. We naturally continue from the Born series picture and head over to see what are the Feynman rules, how these are analogous to electrical circuits, and we try to understand how it's effective in our description for scattering processes. Having understood all of this, we then head to collider mechanics, where we dive deep into the electronics behind colliders and their various other mechanisms, and what happens post collision, that is the statistics and the analysis, with a few examples such as the Higgs and the diphoton anomaly. After this, we deep dive into spontaneous symmetry breaking and how this leads to the Goldstone and Higgs models, where we try to understand the Higgs mechanism, which is arguably one of the greatest successes in theoretical physics. And we'll basically break down the theoretical framework that is behind it, the group theory aspect of it, the field theory aspect of it as well. Then we'll head for a two-part lecture series, a mini lecture series of sorts within this, on the Dirac equation, where we dissect it. First, we start off by understanding the representation theory aspect of it. This would be part 1, and then we head towards understanding the interpretations of the Dirac equation and how one would solve it and what its solutions actually mean to us, and how this again brings us back to the TCP theorem, charge conjugation, and parity, and so on. So yeah, we hope you enjoy this, and this we hope would serve as an enlightening journey for you all. Do let us know in the comments below. Thank you.